Hello, my students. Today we are learning back titration. The back titration that we are learning is the same lesson that we have learned seen in our equation lesson 27, and this lesson they are same. There is nothing different. So what I want you to understand in this case here is that back titration is totally different with simple titration. I already explained that back titration deals with the reaction of acid. First we react acid and carbonate. Then when we react acid and carbonate, we will get a product. And that product we get, we further react with base. And now what's reacting the base? Already acid, we have reacted with the carbonate. Somebody may ask that question. So to answer that question, when acid is reacted with carbonate, there is still excess acid that remains unreacted. So therefore, that excess acid which is unreacted will further react the base or neutralize the base to form a new product. So that's what we call it back titration. Therefore, back titration involves three solutions: an acid, a carbonate, a base, three solutions. So understand it that way. According to this question now we have here, we have this question. We have, you are provided with Fa 3 point, this is 3 not comma, this is point, 3.2 molar of hydrochloric acid. Fb is 0.1 molar of sodium hydroxide. C, we have solid G, which is 1.06 gram of metal X carbonate. X carbonate, we don't know the value of X, but X is carbon element because it's receiving a valence 2 from the radical carbonate. That's what we know only, but we don't know the value of X. Which metal is it? Is it sodium? Is it potassium? Is it lithium? We don't know. So we have procedure here. In the first place, what you do is that you take 10 centimeter cubic of the hydrochloric acid, then you place in a clean beaker of 100 ml. Then after that you add solid G. Solid G, you add all of it, and then when you add solid G, this is acid and this is solid G is carbonate. When you add them, then there is a reaction, and that reaction is the product form is acid reacting with carbonate. The product is salt, which is sodium, which is X chloride, we don't know, plus carbon dioxide plus water. Due to the production of carbon dioxide, there is a production of effervescence. So you stir. Stir means you shake by using a stir rod. You stir it until all effervescence stops. After the effervescence stops, the reaction is over. Then you add still water up to the mark, meaning that you fill the volume of the beaker. So that means it was, the volume was 10 centimeter cubic, you diluted up to 100 because the beaker is 100 up to the mark. That means the new volume formed is 100, and since you formed a new volume, then you label it. You label it as a solution FC because you have prepared a new solution, not from the original. The original solution was called Fa, which was 10 centimeter cubic. Because you have diluted and you have added another compound, you have prepared a new solution, then you label it as FC. So fill the burette with sodium hydroxide solution. You fill the burette with sodium hydroxide solution, then you add 2 drops of methyl orange. You fill the burette sodium hydroxide solution. Then after you fill the burette with sodium hydroxide solution, you pipette 25 centimeter cubic of FC, the new solution that you have prepared. You pipette, and when you are pipetting this solution, please be careful because the solution contains excess acid. If it touches in your tongue as you are pipetting, if you are using your lips, it can cause some corrosion, so take care. So FC, and clean in a clean conical flask. Then you add 2 drops of methyl orange, which is an indicator to show the color. Then you fill the table. Here we have the final burette reading. The final burette reading is here. We got 15.1. The initial was 0.0 of the burette. Then we subtract the final minus the initial, we get 15.0. Here also we have 15.1. Then the initial 0.0, we subtract, we get 15.1. The same here, the same here also. So then the questions, let us see the questions. The questions here, due to time, I'm not showing you to calculate in front of you because the question is very big, and my screen recorder only 15 minutes, and it's not enough for the 15 minutes I to calculate while I show you. I have already calculated the questions here. Okay, the questions are calculate the average volume of sodium hydroxide used. To calculate the average volume of sodium hydroxide Roman 1, you add 15.1, 15.1, 15.1 divided by 3. So if I show you back, This here we have 15.1, 15.1, 15.1. All of them, you add them, then you'll say divide by 3. So 15.1, 15.1 divided by 3. All of them, when you add them, you'll get 45.3. Then divide by 3, you'll get 15.1 centimeter cubic of sodium hydroxide solution used. This is the volume of sodium hydroxide solution used to react with the acid. That is Roman 1. Roman 2, we have calculate the number of moles of sodium hydroxide used. To calculate the number of moles of sodium hydroxide used, sodium hydroxide, what do we have? We have the molarity 0.1 molar, and we have the volume used, which is the average volume. So average volume is the volume of the base, you see, used, meaning that any volume that you are getting from the table is the volume of the base used, sodium hydroxide. So to calculate now, you take the molarity of sodium hydroxide, which was 0.1. 0.1 is equal to 15.1 centimeter cubic, which is the volume used. How many moles will it be equal to? X, we don't know. We cross multiply. 15.1, you multiply this one, 0.1 times 15.1, then you divide by 100. Then this is what you will get. This is the value you will get. That's the Roman 2, how to calculate it. Question 3, it's asking the number of moles of the hydrochloric acid used. So to calculate the number of moles of hydrochloric acid used, since you have the number of moles of the base or sodium hydroxide that reacted the acid, to calculate the other mole of the other solution, you react them. Sodium hydroxide solution plus hydrochloric acid, then you'll get sodium chloride plus water as reacting base, salt plus water, neutralization reaction. So you balance. When you are balancing the equation, you leave all reactant products and reactant side, all elements, you balance it. So when you balance, this is already balanced, and the mole ratio is 1 to 1. Since the mole ratio is 1 to 1, the number of moles of the acid also remains the same, which is 0.00151, the same with this one, with the base. Then that's how you do the second question, question Roman 3. We have question Roman 4. Question Roman 4, in this case, question Roman 4 is asking the number of moles of the hydrochloric acid in 100 centimeter cubic of solution. So to calculate that, the number of moles of hydrochloric acid in 100 centimeter cubic of solution, what do you do? So here we have, this is the number of moles of the acid used. Is it? Yes, in FC solution FC. So what is the volume of solution FC used? Let us see it. We will go it to the next. The volume of in the procedure we have, using a pipette, place 25 centimeter cubic of solution FC. So the volume of solution FC used, of the acid used, is 25. And here we have the number of moles used. So the number of moles used from here, from the equation that we obtain, 0.00151 moles is equal to 25 centimeter cubic. What about 100? This 100, how many moles will it be equal to? So that's what they're asking question 4. So then you cross multiply 100 times 0.00151 divided by 25. Then this is what you will get. This is the number of moles of the excess acid. Yes. Then we have the next question, without wasting any time, question Roman 5, asking the number of moles of original hydrochloric acid, the original hydrochloric acid in 10 centimeter cubic. So the original volume of the hydrochloric acid, before we reacted anything, the original moles was 10 centimeter cubic, and the original molarity is what? Is 3.2 molar. 3.2 molar is equal to, which is the molarity of the original, 1000. What about 10? That's what you will do in question Roman 5. In question Roman 5, that's what we do. Question Roman 5 is here, 3.2 moles of the original acid, which is the molarity of the original acid, is equal to 1000, 10 centimeter cubic, how much? Then you cross multiply 10 times this one, then 1000, you put it at the bottom, then you cancel it, then this is what you will get. This is the value that you will get. Then our next question is question Roman 6. Question Roman 6. Question Roman 6. Question Roman 6 is asking the number of moles of the hydrochloric acid that reacted the carbonate. To calculate the number of moles of the hydrochloric acid that reacted the carbonate, you subtract the original moles of the acid that we obtained right now with the excess moles of the acid. Excess is 0.00604 moles, which is the moles of 100. This excess, you subtract the original moles before it reacts anything. So you will say 0.032 moles, which you obtain here, minus the 0.00604 moles of the excess. This is what you get. This is the number of moles of the hydrochloric acid that reacted the carbonate. That's how you do in Roman 6. We have Roman 7, Roman 6, the number of moles of the carbonate used. So how do you get the number of moles of the carbonate used? So you react the acid and the carbonate. You react the acid and the carbonate. So you say X carbonate plus hydrochloric acid, an arrow, X chloride plus carbon dioxide plus water. So this is what will be formed. Then you balance the equation. When balancing, X is 2 here, then 2 here, hydrogen 2 here, hydrogen 2 here, then the rest are balanced. Mole ratio is 1 to 2. Then since the mole ratio is 1 to 2, then and you have the number of moles of the acid reacted the carbonate, then you will say this 2 mole ratio, which is from the acid, is equal to this number of moles. Then 1 mole ratio from the carbonate is equal to how many? From there, you multiply 1 times 0.26, then anything multiplied X will go down. Then you divide, you will get 0.013. Or you can write 0.01. So always you write in 2 decimal place moles, whenever you are writing 0.01 moles. That is the accuracy one. Then 0.01 moles is the moles of the carbonate reacted the hydrochloric acid. So that's how you do it. Roman 6. Then we have Roman 6. We have Roman 7. The Roman 7 is asking the relative atomic mass of the carbonate. The relative atomic mass of the carbonate. For you to calculate the relative atomic mass of the carbonate, this is what you do. How is it relative atomic? How does it is expressed? It's always expressed this the number of moles of the acid. The number of moles of the acid that of the the number of moles of the carbonate, which is 0.01 or 0.13. This number of moles of the carbonate is equal to always the mass. It's equal to the mass of the carbonate. What was the mass of the carbonate given? The mass of the carbonate given is 1.06. Then 1.06 is equal to this number of moles of the carbonate that we obtained through the equation. Then this is 0.01, which is the mole of the carbonate, is equal to the mass. What about 1 mole? So always RFM, whenever you're calculating, it's 1 mole. What about 1 mole? X. Then you cross multiply. Then 1 times this one divided by this one. This is what you will get it. The reason as to why I'm saying like that is because of this. If the RFM of sodium carbonate, sodium hydroxide, assume this sodium hydroxide, sodium is 23, oxygen is 16, plus hydrogen 1. When you add all of them, you'll get 4. What unit do you give? You will say the unit of RFM is always gram per mole, meaning that 1 mole is equal to 40 gram. That's why always the RFM of any compound is always equal to 1 mole. That's why this is the number of moles of the acid. This is the number. Sorry, where is my pen? This is the number of moles of the carbonate, and this is the mass of the carbonate used, and this is the number of moles of the carbonate used. So they are equal. Then RFM always represents 1 mole. 1 mole is equal to how much? Cross multiplication. This is what you get. Then from there now we have question 8. This is question 6, 7, 8. This was question 8. Question 9. So how question 9? What is it asking? Question 9. Question 9 is asking the value of X. To get the value of X, this is what you do. You take the RFM that you obtain, then you keep the compound X2 carbonate, where X2 carbonate, these two, the value that you are looking, the letter that you are looking, if it has a value of letters X, then you make it coefficient. That number, if it has a number, you make the number coefficient. Then these two, we bring it in front. It becomes coefficient. 2X plus carbon, we have 12 carbon plus oxygen 16 times 3. We have 3 oxygen here. Each oxygen is 16. Then is equal to 103. 2x plus 12, then 16 times 3, 48 is equal to 106. Then 2x plus 12 plus 48 is 60. Then is equal to 106. Then this 60 you transfer to the other side. You transfer here, you transfer to here. Then it's becoming minus because this plus will be subtracted. 2x is equal to 106 minus 60. 2x is equal to 46. You divide by both sides by 2. Then you'll get x is equal to 23. So x equal 23, meaning that x is sodium